Here's an interesting differential equation problem. And it looks pretty complicated because we have this sort of this mess at the beginning here. But we kind of know that that's just basically a function, or we consider that a constant or coefficient in front of this derivative here. So we're just going to divide this by the entire expression here. So we're basically just going to put t to the 4 plus t to the third down here, t to the fourth plus t to the third down here. And this is just going to sort of cancel itself out over here. And then from here, what we can see is that we're going to get some cancelizations and simplifications. So let's just go ahead and rewrite this a little bit. dy over dt plus, this will turn into a y over a t plus 1. And this becomes a 5 ln of t divided by t plus 1. Now the next step is to find the integrating factor. And so we kind of have to define what p of x would be. That's just going to be this idea. Here's our y right here. But the surrounding expression would be sort of this, t plus 1 around it. So we have this 1 divided by t plus 1 that is called p of x in here. And we can multiply that by y and stuff. And from here, we're going to want to figure out what e to the integral of p of x dx would be. And if we just integrate this, then we basically get ln of t, correct? So e to the power of ln of, not t, but t plus 1 here. Okay. Now the cool thing is that for these e to the ln stuff, this actually cancels out, and this literally just becomes t plus 1. So that is going to be our integrating factor. We're going to have to multiply that across all three of these pieces here. So we're going to get sort of this t plus 1 over here. And then I guess I'll just put the dy over dt to the left of it here. And then we're going to go ahead and add that. Notice that over here, if we multiply t plus 1, it's just going to cancel out. And we're going to be left with a y. And then if we multiply the t plus 1 over here, that's going to cancel out and leave us with 5 ln of t. For this step, it's really important that we sort of look at this left side and we try to infer that over here, instead of just as y, there might be a times a d of t plus 1 over dt next to it. Because if we were to do this particular derivative over here, we'd notice that the t, if we take the derivative of t, it just becomes a 1. If we take the derivative of that, it just becomes 0. So we're mostly multiplying y times 1 here. This is technically doing nothing. But what we can actually see is that if we have the u dv over dt type of thing plus a v times a du over dt type of thing, and in this case, we can kind of see how we could replace this with like a y here, and this would be a t plus 1. And then over here, this would be sort of the t plus 1, and then this would be the y. So we've literally sort of reconstructed this thing where we took the derivative of t plus 1 times y. What we just did was we basically undid this derivative with respect to t over here of a multivariable function. You can see it's a t plus 1 times the y. We only have the d over dt here, so we had to do the chain rule. And so that becomes this expression over here. And then, well, we basically just had to infer this little piece right here, the d t plus 1 over dt. We didn't really know that was there, but you could take a guess and sort of stick that there, and then you could sort of see how, wait a minute, this whole left side over here is actually just d over dt times t plus 1 times the y. And that is kind of what we have on the left side. On the right side, we just get the same 5 ln of t. We're not done here, though. We need to take another step. So we're going to go ahead and integrate both sides by dt here. And you integrate this one again by the dt. So both sides are going to be integrated by dt. Now, what's again important is that we notice here that what we're doing is we're sort of integrating a derivative. And so when we integrate the derivative, we're just going to sort of undo the derivative. And so we're just going to be left with a t plus 1 times y on this left side over here, getting rid of all this integration stuff. And on the right side, we are going to be left with a 5. When we integrate the ln of t, we're going to get t ln of t minus t, but let's not forget plus c. Boom. On the left side, we didn't really need to put in the plus c because we're just undoing this. We didn't actually do an integral. Here on the right side, we actually did an integral, so we had to throw in the plus c. But now, let's go ahead and use our information we were given here at the beginning, the initial value stuff. So this is telling us that if we have t equals 1, then y equals 2. So let's just go ahead and plug in those values over here. If t equals 1 over here, we get sort of this 2, and then y is supposed to equal 2, and then we get the equals 5, and then here's a t, which is supposed to be 1. ln of 1 is going to be 0, so let's just ignore that. There's like a minus 1 in here over here, and then we have the plus c. And so we can see if we have a 4 plus a 5, then we're going to get c equals 9. And now we can sort of plug that back into our equation. Now, our final equation was really supposed to be this thing, this t plus 1. We have this y equals this 5, this is t, ln of t, and minus t, and there's this a plus c, which became a 9. And we're probably going to want to put this in the y equals mx plus b form, so let's just divide everything by the t plus 1 on both sides. So we're going to get this final answer of y equals 5 times t ln of t minus t divided by a t plus 1. And then we also have the plus c in here, which is supposed to be plus 9. And that is going to be essentially the final answer over here. Whoa.